So, as we said in the last lecture, the carbon detonation supernova is not really the most common kind of supernova. The other kind of supernova that's really more common is going to be a really massive star dying. And what happens is that the really big stars, when the core gets above the Chandrasekhar limit, and of course mostly iron at this point, but when it gets to the point that it's beyond the Chandrasekhar limit, it collapses. And as it does, as it starts collapsing, then you're going to have protons and electrons coming together, and you get neutrons and neutrinos. Now, a proton is not just a proton plus an electron doesn't really make a neutrino, neutron rather. Neutrons are not composite particles. So a neutron is not really a proton electron squeezed together, even though it kind of looks like it might be, but it's really more complicated. If you remember, when we talked about nuclear fusion inside of stars, we talked about quarks. And so the quarks that make up a neutron are not exactly the same as the quarks that make up a proton, and electrons don't have quarks. And so what happens though is that when you squeeze them together, you have so much energy release that you sort of rearrange the kind of quarks that are in there, and you get a neutron. And then to make everything balance out right, we have to produce a neutrino. Again, this is an electron neutrino. And so result is when you squeeze the core together, which has protons and neutrons, and then you've got electrons in there too because you've got atoms. When you squeeze everything together, you end up with something that's mostly neutrons. There's a few protons still mixed in, but it's mostly neutrons. In essence, you've created something that's like a giant atomic nucleus made of mostly neutrons. And so what stops it finally collapsing is something that is about it's going to be something that's almost entirely neutrons, and what's going to stop it from collapsing is that neutrons themselves can only be squeezed so much, and you have degenerate neutron pressure. We call such a thing that used to be the core of a star a neutron star. And remember, when it collapses, it blows everything else away that's the outer part of the star. Even part of the core that's collapsing gets blown away. So it may have a star that's 10 solar masses, but then the core collapses and you get about a solar mass or so neutron star in there. Bigger star, maybe 20 solar masses or so. Originally, you might get something that's a little bit bigger, 1.5 solar masses, neutron star. 30 solar masses, you might get something that's a couple solar mass neutron star. So the neutron star, your typical one's gonna be about a solar mass, but the bigger the star, the bigger the neutron star can be. The neutron star can be bigger and have more mass than have bigger mass than a white dwarf, so it can be well over 1.4 solar masses. But you squeeze it so much, it's about 30 kilometers in diameter. So imagine, one solar mass, the entire mass of the sun, crammed into something roughly the size of, let's just say, Arlington. Okay. So, life of a big star. Imagine a 25 solar mass star. It's about to go supernova. And so it fuses hydrogen and fuses hydrogen for about 10 million years. Now remember, the sun can go for billions of years, somewhere between 10 and 12 billion years. But about 10 million years is as much as a 25 times bigger star would go. It fuses a lot faster, and so after about 10 million years, you've fused up all of the hydrogen. Then you start fusing helium. Fuses helium for about 1 million years, fuses carbon for about 1,000 years, fuses neon for about 3 years. Each step is quicker because each step is less efficient. And so you fuse oxygen for a few months, silicon's only fusing for a few days, and then finally the core collapses. And so the core collapse can be only about a quarter of a second as everything falls downwards to that big chunk of neutrons. And then the outer parts of the star go inside out and start exploding outwards. And then that is where that you would get a explosion that is the supernova. So, uh, so you have a star. It pre-supernova star. It's going through all these nuclear fusion cycles in the middle. Now you don't really see any of that because it's happening deep inside the star. So you don't really see what's going on in the core of the star. You only see the outside, and it takes a while for all the energy and the turbulence and everything to work its way out to the surface. And so what happens is that you end up with this explosion. And the explosion starts off without just a whole lot of advance warning that things are happening, because you end up with the core collapsing, and you haven't even noticed that you've changed the type of nuclear fusion in the middle, because it takes thousands of years for that to work its way out, and these things just happen too quickly. Now, if you happen to be on a planet orbiting this star, then you would notice that the type of neutrinos that are coming out would change. And so as the type of neutrinos start changing, then you'd know that the end is near. So then the star starts brightening as it starts exploding and releasing massive amounts of energy and radiation across the spectrum. When Botta was looking at supernovae, he was looking at it, and he thought, there's maybe 5 or 6 different types of supernovae that he identified. And so that was his idea, about 5 or 6 different types. Later astronomers cut that back initially to 2 types, and they called them type 1 and type 2. The big difference between type 1 and type 2 is that type 1 supernovae are brighter than type 2 supernovae. Type 1 supernovae have, interestingly enough, no hydrogen in the spectrum of them. Type 2 supernovae have hydrogen. So that's your big differentiator, as the hydrogen that you see in there. So type 1 supernova has no hydrogen. Type 2 supernova does have hydrogen. The other thing about type 2 supernova is that our type 1 supernova is it gets bright and then it starts getting dimmer again. The type 2 supernova gets bright, starts getting dimmer, and then it changes how quickly it's getting dimmer. You have kind of this bump in the light curve. And so that means it starts slowing the rate at which it's dimming before finally stabilizing again to like dropping off. And so these are 2 main types, type 1 and type 2. Your book refers to type 1a as a white dwarf star exploding. That's because there's actually more than one type 1 super. And your biggest difference, though, between type 1 and type 2, as I said, is hydrogen in the spectrum.